So in this example, we want to find the electric potential at a point P, which is a height of z above the center of a uniform disk of charge. Okay, and even though it looks like a ring, just know that it's a solid, very thin disk. Right? It's of negligible thickness. And so the strategy here is to come up with a way to conveniently and symmetrically integrate or add up the pieces of this ring, or this disk, rather, I gave it away, that contribute to the potential at point P. Right? We want to do this as conveniently as possible. And having it be over the center of the disk makes our life easy. So I think the most convenient way is to use a ring system, right? Concentric rings, to be exact. Namely, we have small rings surrounded by slightly larger rings, surrounded by slightly larger rings, and then incrementally we'll increase this radius until we reach our, capital R, right? The radius of the actual disk itself. But when doing that, we're actually integrating around the central axis, right? So we're not only increasing radius, but we're also increasing an angle. Whoops. We're also increasing our angle. So we're integrating effectively from 0 to 2 pi every time. So this is a double integration. Okay, so real quick, let me draw a hypothetical ring. Okay, and that is of radius I'll call r prime. Okay, that's r prime. That's the radius of our differential rings. Okay, that will add up from 0 to capital R, the radius of our actual disk. So let's see. This disk is of uniform charge density, which is sigma charge per area. All right, keep that in mind for 1 second. The electric potential for a continuous charge distribution is K times the integral of all of those dq's over the distance from those dq's to the point in question, right? In this case, point P. And so we don't really know the size of these dq's. We don't have a nice expression for dq necessarily straight away. We can put q in terms of our charge density, though. So Q is equal to sigma times A, and the area of this disk is pi r squared. Pi r prime squared. Okay? Now, taking the derivative of this expression, because we need dq, we have sigma times 2 pi times r prime, and then the chain rule, dr prime. And if you notice, that 2 pi, that's our integral d theta from 0 to 2 pi. Right? So that's the angle integration. This is the radial integration. So embedded in here is a double integral. So let's put that expression into our voltage. Now, integral of sigma times 2 pi r prime dr prime. Excuse me. Divided by r, lowercase r, right? That is the distance from, right there, our differential ring to the point in question, P. And so this here, using, that's a right triangle, that is the square root of r prime squared plus z squared, right? Pythagorean theorem. And now we have an integral only with respect to r prime. Constants can be brought out, 2 pi k sigma, and it's a rather, ugly integral, but that's okay. We need limits from 0 to r. Yeah. So you could try and brute force this, right? You could, looks like a U sub, so you could do this by hand, or you could type it into a software online integrator like Wolfram Alpha, or look it up in an integral table. Uh, okay, Sigma, there you go. The answer to that integral is square root of whatever's in the root. Right? That evaluated in the limits. Right? And so those limits, when we plug it in to r prime, right, we have 2 pi k sigma, and then we have, what was that? Square root of r squared plus z squared, and then minus when we plug in 0, and that's just z. Okay, and now this is our answer, right, in general terms, in an expression term, for the potential at point P. Okay. There we go. Thanks for watching.